Okay, last example, example 5. A wall is 1.8 meters high and 1.2 meters from a building. Find the length of the shortest ladder that will touch the building, the top of the wall, and the ground beyond the wall, round to the nearest hundredth. Okay, so we're finding the shortest ladder here. So that's a minimum. This is an optimization question. And so I've defined my variables as x being the length from the ground to the top of the wall, and y being the length from the top of the wall to the building, both in meters. And I'm going to put in theta because I'm going to solve this with trig. So here I did my best at trying to attempt at drawing a picture ahead of time. And of course, it is not to scale at all. Okay, so let's see where I put my variables. I said that x is the distance from the length from the ground to the top of the wall. That's x. I'll use a different color. Okay, there's x. Okay, and then y is the distance from the wall to the building here. There's your y. And then you're like, Malmstrom, when was this ever happen? And I think the scenario is that you think about those places where they are working on buildings and they have all their scaffolding up. And so you'd have your building, of course, this building keeps going. You know that. My lovely building. And so you have this section here that people can walk underneath here that they're protecting because they're doing some sort of work on the building outside of the building. And so, yeah, maybe the ladder's out on the road. Who knows? Okay. So here's our scenario. We have a ladder that's leaning up against the building. It's touching the top of the wall and it's resting on the ground down below. Okay, so I have x being this length right here. What else do I know? I know I'm going to make myself a little triangle here. I know the length of the wall is 1.8. And then I've drawn this second triangle up here, a little bit messy. And what do I know about that? I know that the wall is 1.2 meters from the building. So that would mean the bottom of this triangle is also 1.2. And I'm going to introduce the angle theta, which is in between the ladder and the ground right here. Okay. And because the blue triangle and the green triangle are actually similar triangles, I can use that theta would also be in that green triangle, and it would be exactly the same value. And I am trying to find the minimum length of that ladder. So as it's shown in the diagram right now, that would be simply to add x plus y together. So the problem with this is that we don't have enough information in its current form to either work with x or to work with y. So this is where I introduce the variable theta so that I can work with my SOHCAHTOA triangles here. So if I look at the blue triangle and I'm thinking SOHCAHTOA, x is the hypotenuse and 1.8 is opposite my theta. So this is actually a sine relationship. So I have sine theta is equal to opposite, which is 1.8, over the hypotenuse, which is x. And for my length formula that I'm trying to build, I need it to say x is equal to. So when I rearrange this, I would get that x is equal to 1.8 on sine theta. Well, another way to write that would be 1.8 cosecant theta. So that's what I'm going to use for x. I'm going to use 1.8 cosecant theta. Now, when I look at my green triangle, the one with y, I am going to look and see that the relationship here is not sine, but cosine, because 1.2 is adjacent to my angle. So cosine theta is equal to adjacent over hypotenuse. So adjacent is 1.2 over the hypotenuse in this case is y. When I rearrange that, I get y is equal to 1.2 on cos, which could also be written as 1.2 secant theta. And that's what I'm going to use for y. So let's rewrite our formula for length as x was 1.8 cosecant theta plus y is 1.2 secant theta. So this is just a way to use trigonometry to represent my length. All right, so now that I have a function for the same variable theta, I can go ahead and take the derivative. Okay, so the derivative in terms of theta is 1.8, and the derivative of cosecant is negative cosecant theta cotan theta plus 1.2. Derivative of secant is secant theta tan theta. All right, so this is really ugly. And maybe the better way to work with this is to flip everything back into terms of cosine and sine, because those are things that we're more familiar with. So as we go to find our critical numbers and making this equal to 0, I'm going to write this out in terms of sine and cosine. So I have negative 1.8, and cosecant is 1 on sine, and cotan is cos on sine, plus 1.2 secant is 1 on cos, and tan is sine on cos. All right, we're going to just have to work with this for a little bit before we can even evaluate. So 0 is equal to negative 1.8 cos theta on sine squared theta plus 1.2 sine theta on cos squared theta, and I'm going to get myself some common denominators. So I'm going to multiply this first one by cos squared and multiply the second one by sine squared, and that leaves me with 0 is equal to negative 1.8 cos cubed theta plus 1.2 sine cubed theta all over that common denominator that I just made, cos squared theta, sine squared theta. Okay, so now we're going to find our critical numbers. And remember, we're looking for critical numbers where either the numerator or the denominator would be equal to 0. So when the first derivative is equal to 0 or undefined. So if I look at the denominator first, because that one's fast, cos squared sine squared theta would have to be equal to 0. That would make the derivative undefined. So I have two factors in there. I have cos and sine. So cos squared theta, when does that equal to 0? Well, take the square root, you get 0. When does sine squared theta equal to 0? Take the square root. When does sine theta equal to 0? So we're going to our unit circle. Cos theta is equal to 0 on my y-axis. So pi on 2, 3 pi on 2. And sine theta is on the x-axis, so 0, pi, 2 pi. And if you go back to our restriction on theta, we actually said that theta had to be between 0 and pi on 2, but not be either of these. So all of this is outside of my domain. They're no good. Okay, so that leaves me with solving the second one as negative 1.8 cos cubed theta plus 1.2 sine cubed theta equal to 0. All right, so what are we going to do with this one to solve it? Let's move the cos to the other side. So we have 1.2 sine cubed theta is equal to 1.8 cos cubed theta. And then if I divide the coast back to the other side. The purpose behind that is that I'm going to build myself a tan function here. Okay, so let's do this. Sorry, I don't want to take the 1.8 with me, just the cos. Okay, cos cubed theta, and then that would give me 1.2. Sine on cos is tan cubed theta. Cos on cos is 1, so that would just leave me with 1.8. And then I'm going to move the 1.2, and that'll isolate my tan. All right. So I have tan cubed theta is equal to 1.8 on 1.2, which turns out to be 1.5. So let's just write that. And then I am going to take the cube root. So I get that tan theta is equal to the cube root of 1.5. Not pretty. But from here, I'm actually trying to find theta. So I want to just throw that into my calculator in radian mode, second tan or inverse tan of this number. And that's going to give me my reference angle for theta, which would be 0.85, etc. Okay, and I only really care about quadrant 1 answers. So even if I refer to CAST and tan is positive in quadrants 1 and 3, I have a restricted domain that puts me in quadrant 1. So this is 0.85 radians in quadrant 1. Do a quick check between 0 and pi on 2 that this angle is going to give me a minimum. And I did a quick check. I have a negative and then a positive. So I went decrease, increase. Yay, I got my min. You guys should know how to do that. And then finally, we just need to actually find the length when we have that angle. So the minimum length would be equal to the function that we built at the beginning, 1.8 cosecant theta plus 1.2 secant theta. Now, I don't have a cosecant button, so cosecant is 1 on sine, and my angle is 0.85 blah, blah, blah. Hopefully you saved it in your calculator. And I have 1.2 on secant is cos, so 1.2 on cos, 0.85 blah, blah, blah. So make sure you're not rounding until the very end, okay? Now secant is buddy is cos, not secant is equal to cos. Secant is equal to 1 on cos. All right, and then you're going to put that, hopefully you're still in radian mode, into your calculator very carefully with the good amount of brackets, and we should find that the length is 4.21 meters rounded to the nearest hundredth. And voila, we are done. We can write our statement that says, therefore, the length of the shortest ladder is 4.21 meters. And I'm just going to leave it at that. You could write more information. And that is it. You made it through chapter 7. Yay! Let's celebrate.